Good morning. Now we will start discussion on a new module, gas cleanup. As you know, most of the waste to energy conversion processes like incineration, gasification, pyrolysis, anaerobic digestion etc. produce significant amount of gas streams. We have already discussed incineration, gasification and pyrolysis, and we will discuss on the anaerobic digestions in later on modules. And the gas produced through these processes contain different type of molecules or the compositions varies, and this can be used in different applications also, and for that applications to meet the quality we need to remove some gas components from this produced gas. Like example, if we want to use say syngas produced through gasification process through different routes, so different quality parameters of the gas is required. For chemical synthesis we have to remove all impurities, but for thermal applications we do not need to clean to that extent. So, this is one way to meet the specification of any downstream applications, we need to clean up the gas. Another important point is that in many cases these gases exit into the environment, whereas the gas contains many polluting components also which make health impact. So, to reduce that health impact or environmental pollution, we need to treat the gas. So, in this module we will cover all those aspects, how to remove different components of a gas before it exits to the environment, and we will make discussion on typical composition of gas produced through different routes of waste to energy conversion, processes for removal of unwanted elements from gas, and basically particulates removal, both particulates and gas molecules removal and gas molecules removal. So, now we will start with the particulates removal first. Before that, let us see what are the different types of gases generated in waste to energy conversion processes. So, we have incineration process, we have gasification, pyrolysis of biomass and waste, pyrolysis of waste plastics and anaerobic digestion. So, these are major processes which produce a significant amount of gas streams. For incineration, completely gas stream is produced. So, the typical gas composition is CO2, H2O, NOx, SOx, particulate matter and nitrogen. So, what we need to remove here? We need to remove NOx, we need to remove SOx, particulate matter and carbon dioxide before it gets entry to the environment. Similarly, for gasification, the composition is carbon monoxide, hydrogen, CO2, H2S, COS, PM and CH4 or methane. So, out of these compositions we need to remove CO2, H2S, COS and PM, particulate matter. CO is not needed because this will be used for further applications for chemical synthesis or other applications, or if it is used for heat production then CO will be converted to CO2, that is why CO is not mentioned here. And pyrolysis of biomass and waste, it produces CO, CO2, hydrogen and hydrocarbons containing gas. These hydrocarbons basically C1 to C5 or C6 it gets C5 gets, and then we need to remove the CO2 because other will be having some heating values. So, after that finally CO2 has to be removed. Similarly, for pyrolysis of waste plastics we will get number of gas components like CO, CO2, H2, Cl, dioxins, hydrocarbons etc. and many others depending upon the use of additives in the plastics. So, we have to remove CO2, HCl and dioxins. For anaerobic digestion we can get gas, biogas. So, that will be containing mainly CO2 and CH4. Apart from this, small amount of H2S and H2O are normally available. So, we have to remove H2S, CO2 and H2O. So, these are the elements we need to remove. So, here we see PM, and other gas molecules. The CON and COS and H2S removal from the gasification gas, that is syngas, we have already discussed in our gasification module. So, we will concentrate on PM, CO2 removal, NOx and SOx removal. So, for the removal of particulates, we have number of equipments, that is gravity settlers, cyclones, electrostatic precipitators, filters, that is bag filters and fabric filters. So, these are important devices which are used for the removal of particulate matters from any gas stream. For gas molecules, wet processes, absorptions and adsorption based processes are used, and particulates and gas molecules, wet scrubbers are used. Both these wet scrubbers can remove both gas molecules as well as the particulates present in the gas stream. Now, we will see the gravity settlers which is used to settle the particles from the gas stream. So, here let us see a gas is getting entry into this settling chamber. So, this particle will be having one velocity, that is equal to say gas velocity, and there will be some relative velocity between gas and particle. So, this velocity is there in horizontal direction, and gravity is also working on it in the vertical direction. So, it is experiencing two forces. So, resultant force will be giving us the resultant velocity. So, this tangential movement this particle will have. So, after travelling certain distance, it will reach to the bottom of it and it will be collected. So, this is the mechanism of the separation of particles in a gravity settling chamber. Now, these chambers are not very efficient, very fine particles cannot be separated by this chamber very easily, and particle size more than 50 micron are normally separated through this. That is why this is used as a pre-cleaner step. But advantage of this process is that this is a very simple process, operation is very simple and its maintenance is very low. Now, we will see how can we design one gravity settler for getting the separation of particulates from a gas stream. Let us see, from a process one gas is coming out. So, we are designing some settler, so where the particles will be settled. Okay. So, let us say this is the length of the settler and this is the height of the settler. So, this particle, any particle if we consider here, that will be having one velocity this direction, that is v of the gas velocity, and that is Vt, terminal settling velocity. Now, if a particle is present here and another particle is present here, so both are having v and this distance, maximum distance is h. So, if we provide certain time that this particle moves in this direction certain distance, and during that time it also travels across the vertical direction is equal to h distance. So, this particle will be separated. So, if these two particles are having same diameter, within this time this particle will also be separated, because the distance required to be travelled by this particle is less. So, we are assuming here the maximum possibility for the separation of all particles. Let us assume one particle is here, so it is travelling h distance. So, this h distance is travelling in vertical directions, and if I want to separate it from this chamber, so it is necessary. So, within this time this particle must travel this one, not more than this. If it is not, it is more than this, then it will not be separated. So, the boundary condition is that, so h by Vt, that is equal to time required to travel h distance from this by the particle. So, by this distance, that is equal to L by V, L by V, V is the velocity of the particle in the horizontal directions. So, this is the condition which will give us the separation. So, now if we know the Vt, then we can get the value of L, at which L or at which will H, what value of H will get the separation of the particles. That means it is giving the dimensions of the chamber. Now let us see how can we get the value of Vt. Vt is the terminal settling velocity. If we fall a particle from the rest, the particle will increase its velocity and attain a constant velocity. So that constant velocity is vertical directions, that is called terminal settling velocity. So we are assuming the same situation here. The particle has reached the terminal settling velocity. So in this case, how can you calculate the terminal settling velocity? You see here Vt is equal to root of 4g dp rho p minus rho g by 3 cd rho g. This is the definition of the Vt that has been derived on the basis of mass force balance on the particle. So I will discuss just now. So this is the case, we can get the Vt, this expression. Now this Cd is the drag coefficient, Cd is the drag coefficient. So Cd is equal to 24 by Rep, the particle Reynolds number. So Cd is equal to 24 by Rep, Rep is your particle Reynolds number. So particle Reynolds number, that is rho d rho dpv t by mu, that is your g. So rho dv by mu. So this is the definition of Rep. Now if we put this definition of Rep, so Cd equal to 24 by this one, then we will get this part, then we will get this part. Now let us see where from this Vt equal to 4g dp rho p minus rho g by 3 cd rho g is coming. Let us see, one particle is there. So this particle is experiencing one force, that is Fg, that is equal to m into g, mass of this particle into acceleration due to gravity. It will be experiencing some buoyancy force, that is Fb, it will be experiencing some drag force Fd. So Fd is drag force. So particle is falling opposite directions, it will be experiencing one force, that is called drag force due to friction basically, and this is due to buoyancy or replacement of volume, it will give the fluid will give some upward force also, that is Fb. So now what is the balance of the forces? The force is that Fg minus Fd minus Fb. So that is equal to resultant force, the resultant force F is equal to this one. Now if F has some value, then it will give some acceleration to the particles, so that will be m into A say acceleration. But when it reaches the terminal settling velocity, that means there is no acceleration, so that is equal to 0. So in that steady state we will get Fg minus Fd minus Fb equal to 0. So we will be getting Fd is equal to Fg minus Fb. So we are getting mg, here we see getting mg, and this is we are getting m into rho s into rho f into rho f g, that is your this one and this is your this one, and this Fd is equal to say Fr. So Fd is sometimes called Fr, that is kinetic force, Fr is kinetic force, and Fr is equal to this Fr is equal to A k into Cd, where A is the characteristics area of the particles and K is the characteristic kinetic energy of the particle and Cd is the drag coefficient. So if the particle is spherical one, then A value is equal to pi dp square by 4, K value is equal to half into Vt square into rho g into rho g. So this is the K values. and CD value we will put CD value we are having CD. So, if we this put equal to 0, so Fr is equal to we are getting mg m into g into 1 minus rho f minus rho s. So, this is the expression. Then if the particle is spherical one, so m is equal to pi by pi dp cube, pi by 6 dp cube g into 1 minus rho f minus rho s, 1 minus rho f. Okay. Then if we are getting this side, and if we now put the Fr is equal to this one A, K and CD, that means pi dp square by 4 into half Vt square rho g into CD, then we are getting by these expressions, by rearranging we will be getting Vt is equal to root over 4g dp into rho p minus rho g divided by 3 CD rho g. So, this is the expression we are getting from the force balance on the particles. So, we can get the value of Vt equal to this much. Now, we are coming to electrostatic precipitator. So, electrostatic precipitator, you see what is the mechanism of separation here? In the gravity separation, gravity settler, we had seen that particles is falling and it is reaching to the bottom after certain time. But when we will be using electrostatic precipitator, the particle will be attracted by some force. One is your negative surface, another is positive surface. We are sending the particles through this. This particle is having negative charge surrounded by it. So, this will be attracted by this surface, and once this is reaching this surface, it will be settled. So, these two are horizontal, these may not be horizontal, this may be a vertical plate also. And electrostatic precipitator are basically of two types. One is your this one, that is parallel plate type. So, these two parallel plates are used. So, two parallel plates are there. So, through this the gas is coming. So, this is gas is coming, and in between these two parallel plates, two electrodes are there, that is your negatively charged, and these two plates are positively charged. So, that this particle is negatively charged, so that will be moving toward the two plates. So, this is the mechanism of the separation. Another type of ESP is available, that is called your wire and pipe precipitator, wire and pipe precipitator. So, what happens in this case? Say one pipe is there, say we have put here some electrode with negative charge, this is with positive charge. So, we have collected here these two and this is to this one, say positive negative. So, that way we have collected. So, when the gas is coming, particle is coming here, so that will be moving to these directions and settled. So, two types of ESPs are available. So, this is gas in, the gas out, the particles will be attracted by the surface due to the negative charge on the pipe. This is the mechanism. So, here interesting thing we are getting that if we take this zone, so one particle is getting one velocity, that is the gas velocity, one is your gas velocity, the gas when it is coming in it will be having some velocity here, and the charge and the surface of this plate or the pipe will generate some electric field and that field will give some velocity. So, this velocity is called drift velocity. So, drift velocity, that is Vpm is generated and V is available with the gas stream. So, these two velocities having, and again one resultant velocity it will be gaining. So, the particle will move, particle will not move directly from this in this directions, it will be having some trajectory. So, now what will be the efficiency? Let us say if one gas is coming here having different particle size and different particle size as well as the charge is different here, the charge is different here. So, positive charge is similar, here the negative charge is more. So, that particle will be moving faster because Vpm will be higher than this particle. So, all particles will not be separated equally. So, there will be some efficiency of separation. So, that efficiency of separation can be explained in terms of efficiency is equal to 1 minus exponential minus Vpm AC divided by Q. What is that? This is the Q, how much gas flow rate is coming. Okay, this is the area of where the particles are collected. So, that is AC collection area, and Vpm that we have discussed, that what is the drift velocity the particle is getting. Now, what is the Q? Q is equal to, say we have two plates here, similar sized plate we have separated by some distance, we are sending gas through this with particles, say we have some volume of the precipitator. So, volume of the precipitator will be V and Q is the flow rate. So, now if this is the L is the distance, and V is the gas velocity, small v is the gas velocity. So, what we will get? Q into L by V. L by V is the time, this is the L and this is small v. So, L by V is the time required to travel the gas molecules from this to this end. So, that time multiplied by volumetric flow rate, that will be the total volume of gas which is passing through these two plates, that is actually the volume of the ESP. So, Q into this equal to V. So, if we replace this expression of Q here, so we are getting eta is equal to 1 minus exponential minus Vpm into AC L divided by Q is replaced by your V into capital V. So, this is the efficiency of this. Now, what will be the AC value? What will be the AC? AC is the collector area. So, collector area. So, if it is a plate type, then area by volume is equal to 2 by S. How it is? We have two plates, the distance is S, So, area is equal to 2 into AC, this is AC and this is AC. So, 2 into AC, that is collecting the particles, and what is the volume? AC into S. So, that is equal to AC into S. So, that is equal to 2 by S. So, area by volume is equal to 2 by S, but if it is a say tubular type of precipitator, then what will be the area by volume? So, area by volume in this case, the area collecting area is 2 pi r. So, 2 pi r into L distance divided by volume pi r square L. So, this is cutting. So, we are getting 2 by r, that is equal to 4 by d. So, that is the case that AC by V equal to 4 by DC and this is by AC by V equal to this 2 by S. So, by the geometry the dimensions of this precipitator, we can get the value of AC and we can calculate the performance. And that VPM is another dependent on the EC, QP and C. QP is equal to particle charge, EC is equal to electric field strength and C is equal to Cunningham correlation factor, that is again dependent on the mean free path of the gas molecules. So, that way if we know these things, we can calculate the VPM and VPM can be used to calculate the efficiency. This is an example. A municipal solid waste based power plant is emitting 45,000 meter cube per hour flue gas. It is proposed to install an ESP with a collection efficiency of 96.8%. Calculate the total area of the collection electrodes. If the collection efficiency is 99.5%, how much additional collection electrode area would be needed? Drift velocity of the particles has been determined experimentally as 0.13 meter per second. So, BPM is equal to 0.13 meter per second, our Q is equal to 45 meter cube per H. So, that has to be converted to meter cube per second. So, that has been converted to meter cube per second. So, if we use the efficiency expression here, so BPM value is given, Q value is given. So, we can get the value of AC as efficiency is given. So, first case we will get the AC is equal to 330.96, for the second case we will getting the AC equal to 509.45 as the efficiency changing. So, by difference of these two ACs we will give the additional area requirement. So, 178.49 we are getting here. Now, we will go to discuss on fabric filters or bag filters. So, in fabric filters, so dust laden gas comes in the bag filter unit and it passes through these bags and it is purified and clean gas goes out from the unit. This has some efficiency is greater than 99.5%. This is the highest efficiency of among the all devices used for the separation of the particulates from the gas. But this is low pressure drop and the fabrics are made of cotton, nylon, polyesters, fiberglass or asbestos. There are four type of separation mechanism, that is inertial collection, interceptions, Brownian movement and electrostatic forces. The particles how these are separated in the bag filters are described here, and in the bag house when the bags are filled with the dust on the surface of it, then it needs to be cleaned, and so mechanical shakers, reverse gas and pulse jet is used for the cleaning purpose. And if we get different types of cleaning, then requirement of feet cube per minute per feet square, that means the air to cloth ratio, how much air can be cleaned by 1 feet square of this cloth is different. So, it is maximum for pulse jet. So, pulse jet is the superior among these, and not only this, the pulse jet can also help the continuous operation of the process. So, this is the most advanced methods out of these three. This is the cyclone separator, another device which is used. In this case, particle laden gas is getting entry here, and due to high velocity it is entering into the cyclonic on the cyclone shape duct. So, when it will device, so it will be getting some movement here, that is centrifugal force will be acting on it, and this will be, and gravity will also act on it. So, this will come in this fashion and it will goes off from the top. So, very fine particles will goes up, the bigger particles will be separated. Again the same mechanism, the centrifugal force will give more velocity towards this. So, m v square by r. So, m is more means force is more. So, bigger particles will be separated, come fast to this surface and will get separated. Finer particles will not be able to come here and it will goes off. And for the separation, the condition is that the particle diameter must be more than 0.2 do. So, this is the do or the diameter of the outlet pipe. So, this outlet pipe is having 0.2 do. If the particle size is more than that, then that can be separated through this cyclone. So, here different types of forces work on the particles, centrifugal force, drag force and gravity force also. The expressions are given here, and these are the laminar gravitational free settling velocity, already we have discussed these things, and minimum size of particles for separation in cyclone separator. What is the minimum particle size that can be separated from this separator? That is that can be calculated through this empirical relationship. dP minimum is equal to 3.6 A I squared dO rho g mu g pi z d rho s and g. This g is equal to mass flow rate of gas. So, this is the mass flow rate of gas is g, and then A I area of the cross section of the gas inlet, again the area is of cross section, that is equal to A I. Next is your dO we have already explained, and d and z we have to know. So, this is the diameter of this part, the cube cylindrical part, the diameter is d, and the cone shape part diameter is different from this, and we are having the total height is z. So, z by 2 is conical part and z by 2 is the cylindrical part. So, this is the conventional design of these cyclones, and if we know the value of z, we can calculate the dP minimum, which can be separated from these cyclones if these values are known to us. Now, this is the slide which give us the comparison of the efficiency of different types of devices like gravity settler, ESP, fabric filter, cyclone separator, etc. We see a different typical your particle size ranges which can be handled by these systems, and the removal efficiency is also different. So, from this it is very clear that fabric filters is having the maximum efficiency and it can remove very fine particles also. But all the processes have their advantage and disadvantage. So, up to this in this part of this module. So, we will discuss the rest part in the next module, in the next part of this module. Thank you very much for your patience.